So we're going to be looking at graphing transformations of special functions again this week. We're going to take everything that we did last week, the reflections and the translations, and we're going to put them together today. We're also going to look at dilations of special functions. But you essentially have most of the tools, in fact all of the tools really, that you need in order to do the assignments for today and tomorrow. I'm going to start you off with a couple of examples of mixing up what we did last week together into the same problem and show you how that looks. And then we're going to do some examples on dilation. I'm going to let you work together in your small group, and then finally you'll have your independent assignment that will be due on Wednesday. You need to have out a piece of graph paper if you don't already. You need to have a pencil. Everything that I write down in the video, you need to write onto your paper. These are your notes for today. You need to have those to help you with your assignments. Okay, for the first example, I've got f of x equals negative of the absolute value of x plus 2 minus 1. First thing we're going to do is we're going to diagram the function just like we did last week. The negative in front means it's going to reflect across the x-axis. X plus 2 means that's our horizontal shift, and it's going to go the opposite of what it looks like. So plus 2 means it's going to go left 2 units. And the minus 1 at the end is our vertical shift to tell us to go down 1 unit. So we're going to start with the parent function, which would be the absolute value function in this case. And I'm going to take that function, I'm going to reflect it, move it left and down. Now, if you have reflections and translations both in your function, you always need to do the reflection first, then the translation. So always do the reflection first, followed by the translations. If you do the translations first then reflect it, it's not going to be the same graph. So, go ahead and graph your reflection of your parent function. You can probably do that without graphing the parent. Graph the reflection onto your paper. The reflection of the parent function will look like this, goes through the origin, reflects across the x-axis. Now, if I were to take this and take my reflection and move it left 2, down 1, that's simply going to be taking this reflection here, moving it left 2 and down 1. So every point would move left 2 and down 1. So the vertex would move left 2, down 1, and all of the other points on the absolute value function. So I would start here. And I could simply just draw my absolute value function in there. I'll go back and erase what I had earlier so that it's obvious which one my answer is. Okay. So this is the graph of f of x. I reflected it and then I translated it. Look at the second example. I've got 4 minus x squared. So in this problem, g of x is going to have a parent function for the parabola. And if I diagram this, I've got 4 on the outside. Well, that would be the same thing as negative x squared plus 4 on the end. So again, this is our vertical shift, up 4. And notice that in front of the quadratic you have a negative, or here in front of the x squared there's a negative. And so you can think of this as -1, or you can think of it as just the negative that makes it flip. And so the negative is outside of the x squared, not paired with it, so the negative is going to make it reflect across the x-axis again. So, take your parabola, flip it upside down. You can probably graph that without going back to the parent. And then from this point, take all of your points that you used to graph your parabola and move them up 4. Easiest thing to do is to take the vertex and move it up 4, and then graph your upside down parabola from there. So on my graph, I have enough room to keep going all the way to the next point. You might not, but that's okay. If you have room, keep going. Remember that your parabola needs to be aiming towards where the next point would be if you don't have room. Erase the original function, and here's your answer. We also want to look at dilations. Dilations are a way of taking your basic shape and making it flatter or skinnier, things like that. Now, unfortunately, for dilations, there's a couple of things that we can take notes about the nature of the dilation. However, to get an exact graph, you're going to need a table of values. So this is one of those things that if you want a good graph, you need that table of values. We can look at the function and tell if it's going to be fat or skinny, and we definitely are interested in knowing that in all of our topics for the rest of this year, plus those of you who are going to be with me in pre-cal next year, that'll be a very important thing to know from looking at the function, if it's skinnier or fatter. But we do still want exact graphs, so we're going to need tables for this. I'm not going to ask you to do crazy tables. I just want to know that you know the concept on this. So here are 2 examples that I might give you. Okay? F of x equals 1/2 x squared. Let's look and see what happens if I make the table plug and chug. Now the translations, the reflections, they still work. The 1/2 in front of the x squared is going to represent my dilation. It's going to do something special to my graph. Let's go ahead and make the table and see exactly what it does. Okay, so I'm going to plug in values for x. You want to plug in strategic values so that you get nice numbers to work with. But in this case, we should be fine. Now, since my graph does not have any translations, doesn't go left, right, up, or down, I know that the basic parent function was centered at the origin, and so I'm probably going to make a table where my x values are around the origin. That's just being smart about picking x values. Remember, you can do any that you want as long as you get the full picture. Now, if I plug in these values, if I plug in -2 for x, I have 1/2 of -2 squared. -2 squared is 4, half of 4 is 2. If I plug in -1, -1 squared is 1, half of 1 is 1/2, or 0.5. If I plug in 0, 0 squared is 0, half of nothing is just nothing. Again, if I plug in 1, 1 squared is 1, half of 1 is 1/2. And if I plug in 2, 2 squared is 4, half of 2 is 2. Okay? So I plug and chug with the order of operations, and now I'm going to plot these points. So -2, +2, -1, 1/2. So estimate that would be about halfway in between the origin, 1, 1/2, and 2, 2. And so you can see the parabola forming up. And notice how this compares to the actual parent function. Remember, your parent function went through 0, 0, 1, 1, 2, 4. And so this green graph is the parent function. And we want to compare the two graphs. It looks like the 1/2 x squared is a little bit flatter than its parent. Okay? So it looks like the 1/2 made the graph flatten out a little bit. And that's what's going to happen if you have a 1/2 or something less than 1, some fraction, in front of your parent function. It's going to be a little bit flatter. So if the coefficient of the coefficient of the parent function is between 0 and 1, so if the coefficient is between 0 and 1, then the parent function will be flattened, for lack of a better word here. It's going to flatten out. Let's look at what happens in g of x. If I have g of x equals -3 times the absolute value of x minus 4, I'm going to plug in values. But this time I'm going to be strategic about this, okay? I know that my translation things still hold, and I know that my reflection still holds. So I know my graph is going to be reflected across the x-axis. And the -4 means my graph is going to be translated down 4 units. So my absolute value graph is going to be upside down, and it's going to be pretty low on the graph. I know it's going to start here. So I know that my absolute value function is going to look something kind of like this. Okay? I need to know how skinny or fat it's going to be, and for that I need the table. So I know that I'm going to start drawing my absolute value here at x is 0. So 0 is a good number to put in the middle. So -1, -2, 1, and 2. I'm going to plug these numbers in to g of x and evaluate those. So if I plug in -2, the absolute value of -2 is +2. -3 times +2 is -6. -6 minus 4 is -10. And I probably don't have -10, but at least I know that's the point I'm going for. -1. Absolute value of -1 is 1. -3 times 1 is -3. -3 minus 4 is -7. So I plug in 0. 0 times -3 is 0. 0 minus 4 is -4. I already have that point anyway. So that just confirms that I'm right. If I plug in x is 1, absolute value of 1 is 1. 1 times -3 is -3. -3 minus 4 is -7. And if I plug in 2, you can probably guess from the table what I'll have. But absolute value of 2 is 2. Negative 3 times 2 is negative 6. Negative 6 minus 4 is negative 10. So I'm going to try to graph as many points of these as I can. So negative 1 is negative 7. 1, negative 7. And I don't have enough room to graph negative 10, but we know where it would be, and so our graph is going to go in that direction. So we have this as g of x now. Notice what the original function would have looked like had I not had the 3. If it were just g of x equals negative absolute value of x minus 4, without the dilation in it, it would have gone through the same order, or the same 0, negative 4, and it would have fanned out like this. And so notice the 3 made our graph skinnier. So if the coefficient is greater than 1, then the parent function will be skinnier. Now, that's to say the negatives as well. So I guess I can amend this and say if the coefficient is between negative 1 and positive 1, then the function will be flattened. So if it's a function between, if it's a fraction between negative 1 and positive 1, then it's going to be fatter than the parent. But if the coefficient is not between negative 1 and positive 1, then the parent function will be skinnier. So if the coefficient is not between negative 1 and positive 1, then the parent function will be skinnier. So the idea is that you're able to look at these two functions and know if they're skinny or fat. Where they start on the coordinate plane, left, right, up, down, you can still tell reflections, same thing. It's just now you have a coefficient in front of your parent function, which would tell you if it's going to be skinnier or fatter than its parent. Okay, so here are two small group practice problems. What I want you to do is think independently first about how to diagram and graph these functions. Give yourself at least 30 seconds to think about each one. Then work with your group to complete these problems. If you think you can do it on your own, go ahead and graph them on your own. After no more than 5 minutes working in your group, restart the video and I'll show you the solutions to these before you go work on your own stuff. All right, so here come the solutions. For problem number 1, this should have been the graph you got. I noticed that there's a translation left 1. There's a translation left 1, so, and there's a reflection across the x-axis. So you should have moved it left 1, had the upside down absolute value function. Now since this was going to be the center of my absolute value function, I put -1 in the middle of my table and then plugged in values around that. Your table doesn't have to look exactly like mine as long as you get the same graph. You should have a complete picture. If your values didn't give you the other part of the V, if you just have a straight line, then you need to plug in more values for x to get the other side. Okay, the solution for number 2 looks like this. Notice it's the cubed root parent function. And the cubed root parent function is going the same way because it's still positive. There's not a negative, so I don't flip it. But I do move it down 2 units. When I plug in for my cubic, or my cubed root function, I want to use 1s and 8s because I know the cubed root of 1 and I know the cubed root of 8. Those are good numbers to use. Okay, sorry. I moved my table over so you can see. But, again, use 1s and 8s. And if you use 1s and 8s, you can take the cubed root of 1, you can take the cubed root of 8, and those will give you better numbers to work with. Now, when I take the cubed root, I still have to half it, but we can half numbers. We're good with that. So if you're still not good with this, cubed root of 8 is 2 because 2 cubed is 8. The cubed root of 1 is 1 because 1 cubed is 1. So these are numbers that you should already know. Whenever I plug them into my formula or plug them into my function for g of x, and I plot the points, this is what I get. So your graph should look similar. And should be going towards the point 8, negative 1, which would be on this line somewhere. So be headed that direction. So this is what your graph should look like. All right. Once you're good with those, you have a independent practice worksheet to do on your own. If you need to partner up for the first couple, just to get your bearings, that's okay. But you do need to have all 30 of those functions diagrammed and graphed by Wednesday. Do not try to do all 30 in class tomorrow. You will not get done. Do at least the first 10 today. If you don't get done with them in class today, do them tonight as well. Come in class tomorrow. At least get through the next 10 in class, and then you got 10 more for after class. Pace yourself through this. All 30 are due on Wednesday for your homework grade. We will be moving on Wednesday. Okay? So if you have any questions, you can ask Ms. Stinson, or you can write them down and remember to ask them to me on Wednesday. You should be good just to talk it out in your groups. All right, so have a good day.